Okay. Do you have as an answer 2.3695? Not so yes. Oh, do take time in the picture. You want to do a nice job with the picture. You should definitely store the intersection points, obviously. So easy. All right. So negative 3.414. So negative 0.585. All right. Now we're ready? 2.2. Is that what you have? Nope. Yay. 2.3695 is what I got. All right. Do we all agree? Should we talk about it or no, you get it? Okay. For upper minus lower, yeah, it's slide minus parabola. So x minus 2 minus x squared plus 5x. Okie doke. Cool. Boom. All right. Check this out, my friends. Today we're, you don't have the notes. Do you have the notes? All right. Well, I thought, I could have sworn that you knew this, but I just went too fast and I said, just try these problems and they couldn't do them. So I had to go back and say, maybe they need a little review. So by way of little review, here goes. They won't take too long in the front and in the back. These are two new divisions. All right, my friends. So, ye old problem of the day is this guy, the derivative of the antiderivative, which is, some books call it the fundamental theorem part 1, some books call it the fundamental theorem part 2. I wish I could read the history and remember which one is the actual part 1 and part 2. But what do you say we shoot for the moon, and instead of just slapping some calculations together, let's shoot for true understanding. What do you say? No. Okay. So, consider, why shouldn't we be able to define a function in terms of integrals? Isn't integrating a function something you do? So, I mean, if we can make a graph for square root of x, and we can make a graph for e to the x, why not make a graph for the integral of something? You know what I mean? All right, and just like those involve an action, square rooting means what times itself equals no. An integral defined function is an area accumulation function. G is an area accumulation function. Now, no, I know this isn't in your notes, but it occurred to me, I really wanted you to understand what the heck is going on, okay? So if I ask you to, hey, picture g of negative 2, what does it mean? What does it mean? Graphically. Okay, it's the integral from negative 3 to negative 2, which would mean it represents the area. That right there is g of negative 2, okay? Okay, what if I ask for g of negative 1 visually? And it's the area from there to there, yeah? so far? So G is an area accumulation function. Now, if I were to graph G in this first region, it's gaining, oh, so much area. But in the next region, it's gaining a little more area, yeah? So if I talked about the rate at which area is gained, would you agree that it's gaining rate more in this region than that first region? Okay, why? Why is it getting more area more quickly in the second region than the first? What makes that happen? It's the same width, so that's not it. It's because the height is different, because the height is bigger, right? Gained depends on the function f. Now, maybe we should also get our variables f here. This is the f curve. Sorry, I should have probably told you that. This is a function of u, which is just some dummy variable that makes the curve. X is actually the cut point. It's from -3 up to x. So x on this picture represents the right bound of the region. You follow? You tracking? Are you with me? Okay then. If the rate at which area is gained depends on f, then doesn't that mean that the rate of change in the area accumulation, depends on the function type, or f? So wouldn't it make sense that the derivative of that integral defined function is type f? You follow? All right. Now, let's talk about what if x wasn't just some meaningless variable. Say, instead, x was a boundary that maybe moved, like back and forth, back and forth. Darn it. It's going so well. Try it again. Okay? Now, if, you get the idea. If that boundary moved, then wouldn't the rate at which area is changing depend on two things? The rate, or how high the curve is, but also how the function or the x point moved, yeah? So that if, for example, the G was defined as the area from -3 to some oscillating endpoint under the curve, then the derivative of that would depend on how high the curve is, but how the endpoint is changing, so it's derivative. So in this case, then you've got to change it. All right. Now, all that said, that's what goes through my mind when we do these, but the problems are actually much easier than all that. Are you following me? All right. Say we did this the quote-unquote long way. Not by saying, oh, I know the derivative, the antiderivative, blah, blah, blah. But if we actually took the antiderivative, what is it? 1/3 t cubed minus 3/2 t squared plus t from 0 to x. If I put in x, 1/3 x cubed minus 3/2 x squared plus x minus 0. And therefore the derivative of this would be the derivative of the antiderivative I took, which is actually right back to the original function, but now instead of t being in it, x is in it, right? What about this? This point. Doesn't matter, does it? How would this answer have been different if instead of starting at 0, it started at 1? Would the answer be different? If this were 1, wouldn't this still be some constant, but you take the derivative of that constant, wouldn't it still be 0? So I ask you again, does that number matter? It doesn't. Now, visually speaking, that doesn't matter because I don't care whether I start at here or here or here. The area the rate at which the area is changing depends on where I'm at this point, not that point. I don't care if I started here or there. The rate of change in the area is all about the right edge. All right, now, it's obvious then that the shortcut is that the derivative and the antiderivative are inverses. So with the shortcut then, what is this guy? Sine of x cubed. And what about this guy? So our tangent of x. Now, that's nice. Derivative of the antiderivative or inverses, just put in an x instead of a t. Let's talk about little wrinkles then. Come on, let's go. Let's move along. There we go. Okay. Now, I don't know if we need to do this whole thing the long way. Let's shorten this up a little. Let f be the antiderivative of that guy. Okay? I'm going to call the antiderivative capital F, because I don't really need to find it. It's going to go away in a second anyway. So let's call it capital F at 4 minus capital F at x, where f is the antiderivative. You follow? All right. If I take the derivative on this, then this time I'm getting a zero derivative first, and then a negative of the derivative. So something like the end result being the opposite of the original function with x in it, or negative x squared plus 3x minus 1. Now, could we just as easily have done that by switching the limits and negating? That probably would have been easier. All right, but you get the idea. So what would this be just without all the work? Negative cosine of x cubed. Cool? And this would be negative natural log of x squared minus 3. All right, last but not least, function within a function. If you get a limit of integration, then you're going to have a chain rule problem. Again, I'm going to, rather than actually, I know I can do the antiderivative here, but often in problems like these, you can't do the antiderivative. So it's pretty typical just to use f capital as a stand-in for the antiderivative, though obviously you could use sine. It's pretty easy. But it's capital F at x squared minus capital F at 2. Now when I go to take the derivative on that, we have a function within a function. So when I take the derivative of the outside, that represents the derivative of the antiderivative, which is just the function with x squared in it. So cosine of x squared. But then by chain rule, we would have to take the derivative of the inside. And so we'd have to multiply that by 2x. So if you get it in the other parts of it. So if you get a case where a limit of integration is a function, you have to use the chain rule. So this, what might this be? Without any long way. Natural log of sine squared minus 3 times cosine of x. All right. Would you, I think the first two are pretty, do those three, they don't take long. The last one's a little funky. But you're so smart. How are we doing? Do you agree with my answer? Cool. All right, let's switch gears. Totally different idea, as sometimes happens in Saxon. Just a totally different idea. Two real ideas in this lesson. Log, estimating. Really, this should be, I feel like, a little more universal, not just estimating log, but estimating anything with trapezoids or Simpson's rule. If you were to ask a pre-calculus kid, what's log? What is log? Actually, they probably just shrug their shoulders around. But a good pre-calculus student would be something like it's the inverse of e, something, yeah? Or e to what power is something. Would you agree that is one of the ways to conceive of natural log is to think of it as the inverse of the exponential? A calculus student would not think of log this way. In fact, mathematically speaking, log is defined as the area under the 1 over t curve. That's what log is defined as. If you were to talk about the log of 2, for example, it really means if you were to draw the 1 over x curve or 1 over t curve and start at 1 and go to 2, that area, that's what the log of 2 is. Now, we could actually see that coming. If you were to take the fundamental theorem towards this, it'd be natural log of the absolute value of t from 1 to x, which is the natural log of the absolute value of x, minus the natural log of the absolute value of 1. But the log of x is, the log of 1 is 0. Now, you might say, then what about the absolute value? Now, you actually wouldn't use this definition for a negative. Logs don't pertain to negatives. You would have an improper integral there. So, log of x is defined as the area under 1 over t, 1 over x's curve, that shaped curve. You follow? And you could actually use then that combined with your mini estimation methods to calculate log of 4 without a calculator, as precise as you wanted to. Let's say I wanted to estimate log of 4. That visually means the area under the curve from 1 to 4. So that guy. Now by trapezoids, which follow along pretty well with that curve, this would be approximately equal to, what's the delta if I'm using 3 trapezoids? The total region is 3. I'm using 3 trapezoids, so delta x is 1 times the half. F at what? 1 plus 2f at 2 plus 2f at 3 plus f at 4. Now, from experience, there is one huge source of error for students that they always screw this up. Let's be very clear in your head here. F is 1 over x, not log. Okay? It's stupid on so many levels when I see the first student do this on the test and their work looks like this. Now, consider how stupid this is for 1 second. This student is arguing that the log of 4 is the log of 4 plus other crap. That's ridiculous, okay? That's stupid. That just, no, okay? The curve is not the log curve. The curve, the function is 1 over x. All right? So, be clear with that. This should be no calculator. F at 1 is 1. F at 1, F at 2 is 1/2. F at 3 is 1/3. And F at 4 is 1/4. Therefore, the log of 4 is approximately equal to, what we got there? 2 plus 2/3 plus 1/4. That is 12ths, maybe 24 plus 16 plus 3, or 43 24ths is my estimate of the log of 4. You follow? Alrighty then. Now, We could decide if that's good or bad two ways. We could pick up our calculator and type in log of 4, take away 43/24 to see the difference, which would represent the error. But we could, without a calculator, figure out, a bound on how much error there could be. Now, this I want to talk about. I must not have taught this or communicated or demonstrated the proper work that I want you to see, because I feel like some of your M work is terrible. So let me explain here. You must communicate your M well. This is not scratch work that you're doing off to the side for your benefit just so you can nail the M. You have to communicate, argue why you say M what it is, because that's often a separate point that identifies M with reason, right? So true work should look something like this. First of all, the function is 1 over x, not log. The derivative is negative 1 over x squared, and the second derivative is 2 over x cubed, right? M is the max of 2 over x cubed on the interval of the integral. So from 1 to 4. Well, where would that be at its greatest? At 4? No, it's a decreasing function. So it would be at its greatest at the left edge, 1. So the max is 2. Now, you don't have to do some kind of crazy third derivative test on the second derivative map. You don't have to do that. But you do have to communicate your thinking a little bit, all right? So M equals 2. Therefore, my error is less than the error bound. B minus A is 4 minus 1 cubed. Our max is 2 over 12. Our N is 3. And that is something like a couple of the 3's go away. And 3 and the 2 make it, I'm feeling like a half. How about you? Alrighty then. The error, does that mean the error is a half? No, it means the error is less than a half. Okay? Less than a half. In fact, the error is more like 7 hundredths or something. Or I can't remember what. Maybe that was my Simpson problem. All right. Would you try the next one just to see how you're doing with trapezoid error bound? If you wanted to estimate the log of 10, this time I'm talking log of 10 now. How many trapezoids would you need? Notice it doesn't say estimate the log of 10. It just says before even beginning, how many trapezoids would you need to get error less than 100? What did you get for your M? You're still working. Yeah, 2. Now you might at that point then say, so is this, on these problems, is M always 2? And the answer is no. In what case would M not be 2? It's decreasing functions, so yeah.
If there was a negative?
Can't be negative, but you're going the right direction. If it is less than 1. If you are trying to estimate the log of a half, then that edge would be less or greater than the right edge. Okay, so the answer is if you're estimating log of something more than 1, then M will be 2. But if you're estimating something less than 1, M will be something else. All right, so we want to say, so 10 plus 100. So, to get something like 111 or something like that. All right. 111 or more, obviously. Okay. Would you, last but not least, estimate the log of 5 using Simpson's rule with n equal 4? You should not need a calculator. Let's see how good we are. Okay. How'd you do? Did you get 73/45? Now, at the start of this period, if I would have said, hey, estimate the log of 5, could you have done it pretty well? Okay, now you just got within 1.012 or 12 thousandths away. A little more than 100 dollars. That's pretty stinky. Okay. All righty then. Questions? Oh, are on the homework. How did the old yellow or the fun sheet go? Did you enjoy it as much as I did? I don't know. I enjoyed it quite a bit.
I enjoyed it a lot.
This is, I don't know about you, but this is the first homework I do. I mean, of all the stuff I got to do after school, I need to keep it. That's nice. So, I think it's all done. But, so be it. I feel confident in these answers because if nothing else, Amanda Geek agreed with me, and that's good enough for me. So, tell me if you disagree with anything.
Well, it turned out to be less than all.
What is it? 4 pages? Oh, pages, I get you. I thought you meant
That's
like
funny.
pages.
Oh.
Pages.
These right here, I was like, I'm not doing the page.
Oh, nice. Went back and took two.
I think we don't want to do a 3D.
For the front side F, I hope you found you required 2 integrals, yeah?
Front side of that.
Front side F, because it was a function of y, you had to do it with 2 integrals. not to point out, I know it's obvious, but when you do revolutions, you have choices. Discs and washers allow you, and shells mean that, you know, whatever variable you want to use, you can use that variable. But these, you have no choice. The minute they say parallel to this or that, that determines the variable. You have no choice. So that does make these a little hard. There's no, could go two ways. All right. Let me know what you'd like to go over. Yes, sir.
Maybe 2G.
2G? The 2G, yes, 2G. Gotcha.
You do 3A and B,
3A and 3B. Gotcha.
and also 1B.
1B? Okay. 1A? 1B, okay.
And D.
One-
No, B and D.
1D, 1F,
And B.
and B.
Yep.
All right.
And B.
And E? All right. That's the old script. All right. They take a while. I'm sure my question this probably would have been longer when I was on this the first time. All right, here we go. 2G. 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 All right, so it is the region of the sinusoid and the line. And they're parallel to the y-axis, so check that you have your cross sections identified correctly. And it's a taco problem. Okay, it's like actually one crescent roll made out of a lot of tacos. I'm kinda hungry. All right, so if we should have crescent rolls for educational tool. Oh, this was good. I got a young little buttery. All right, can you tell me what the variable of integration is? Is this dx or dy?
DX.
It is dx. Check. Can you tell me the shortcut for the area of the base or cross-sectional area calculation? Maybe not. Now it's about boiling it down to the diameter rather than the radius. And do you remember that if you put in place of the radius half the diameter, that it goes to pi over 8 of the diameter squared? All right. So if you throw a pi over 8 out of your integral, and you put a square down so you don't forget, and then a dx, then you just start identifying the diameter. The diameter feels like a vertical movement, so upper minus lower will give me a positive quantity. Upper is the sine curve, and the lower is the line, pi x over 2. The limits of integration are x-ish, so the x starting point is 0, and ending point is 1. That's what I did for 2G. Do you agree? Okay. All right, how about 3? Yeah, now if you're a little, are you a little off or a lot off? Okay, I was going to say the first thing is that, okay, if you're like 1,000th off or something, it might be because this lower intersection point, while it is very close to the origin, or not the origin, the axis, it is not the axis. Yes?
For 2G, how did you get pi times x over 2? The function was 2x over pi.
Oh, okay. Well, then it's
Oh, 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 yeah. Did I do that? I think I put that in my calculator wrong. So you got something different for 2G.
Yeah, because I got a different answer. And
I got the answer you got.
Did you have pi, did you put pi x over 2 or 2 over pi?
2x over
Huh. Now, I definitely wrote in my work the wrong word, pi x over 2, but it should be 2x over pi.
I got 0.084.
Really? I don't see my calculus. I had it set up. Sorry, just a second. Thank you. Divided by 8. 0 to 1.
No, it should be 0 to pi over 2.
0 to pi over 2?
No? Yeah. Yeah. It should be 0 to
Oh,
pi
0 to pi over 2. Yeah. Sorry, so I had 2 mistakes. Actually, I had that right in the word. So you, Cass, you got this, but I didn't. So I wonder if I had it wrong on my paper, but I set it up correctly in the calculator.
It's still getting 0.084.
I got 0.140. Are you negative?
Yeah, should be.
Oh, you're not sure. Yeah. Okay. All right. Okie dokie. Are we, so we're cool there? 3A. I was that there.
Yeah.
Okay. 3A. So we got your, okay. This one requires you to do a little geometry. The equilateral I have memorized. I don't really do much of that. But for 3A, do you agree they talk about isosceles right triangles? Yeah. And that means the legs are congruent and it's a right angle. Yeah. Now, if you take that, come here, you. Come here. Oh, this is so much fun when it works, but it's not working. Come on, rotate. All right. So if you take that bad boy and you shrink it down to size, that'll work. Then that's what we're looking at, right? Okay. Now then, when I find the area of that, do I have that parallel to the? Yeah. Okay. Okay. Let's talk about the area of this. Let's actually start thickness. Is thickness dx or dy? Dy. I agree with dy. The area of the base. Sometimes we use 1/2 AB sine C, and sometimes we use base height divided by 2. Now we use this for equilateral triangles because it goes beautifully. You probably wouldn't use it here because, well, yes, these are the same, that's great, but neither one of those is in the plane of the base. And so you probably don't do that. Instead, we go here. Now, here's the base, here's the height. The key by far is getting the geometry right. What's the height's relationship to the base? Let's start with here. What's this angle? It's 45, which makes this half triangle 45, 45, 90. So doesn't this have to be congruent to that? And that implies that the height is half the base. And therefore the area is base times half base divided by 2, or 1/4 of the square of the base. Now, all that geometry work should be done before you go to the integral. Then the integral goes smooth. 1/4, I think the lower limit of y was just a little shy of 4, like negative 3.999. And the upper limit was 0.5-ish, 501, 4. All right. Now I got the fourth out front. I need to square the base and dy. So what is the base then? Is that a horizontal or vertical distance? So it's right minus left. What's the right? It's the cube graph in x terms or y terms? Y terms. So what is y equals x cubed minus 4 in y terms? cube root of y plus 4 for the right. And then the left is the log graph in y terms. So e to the y. So I'm feeling like this, it would be the square of the cube root of y plus 4 minus e to the y, that quantity all squared. I wrote that badly, but you get the idea. Okay, cube root of y plus 4 minus e to the y, quantity squared dy. All right, how about 3b? 3b? 3b, it does not read the same. It says isosceles right triangles, but with the leg in the plane of the base. So if I put the leg in the plane of the base, is it parallel to which one? Oh, parallel to the y-axis. I can't do that here. Oh, well, you can do it. All right, so parallel to the y-axis would look like that.
Yeah.
All right, so for that area, is it dx thick or dy thick? Dx thick. Area of the base, this time base height divided by 2 goes beautifully. It's because what's the relationship between the base and the height? Because it's isosceles, and the leg is in the bottom, the base and the height have to be the same, yeah? So this is 1/2 base squared. So 1/2 the integral, the square is the base rather is now a vertical distance, so upper minus lower. What's the upper? In log, natural log, minus the cube. Quantity squared dx, and I think the limits there are a little above 0, 0.00 something or other. For the left side, it's just to the left of the axis, 0.18 and 1.651. Checkity check. All right. 1D, is 1D still a question for me? 1D. I tried so hard to make this picture pretty, but it didn't turn out. I was not happy with it. Actually, revolutions I don't usually draw from perspective. Let's try it, shall we? Here's the area from 0 to 1, okay? Or here's the area, right? And here comes the revolution. It's around that figure, yeah? So, if I'm not mistaken, the figure when it's revolved will look something like oh, this is terrible. I don't like it. Oh well. Did you use X or Y? You should definitely want to use X because Y would be 2 integrals, yes? So if we use, if you use Y, I guess we could do it with Y washers, but you would require 2 integrals. Do it with Y?
But I don't know. Well, you can do it with
X is much better. You should do it with
I'm
X. Okay, that was probably your error.
I did 2 intervals.
At least, oh, that's good, but why would you want to do more work? That's weird. Okay, so, I don't like it. It's a shell if you use X. And what is the radius? 1 minus 6, or 5 minus 6, right? 5 minus 6, okay? All right, and what is the height? The height is here, and isn't it the upper curve minus the lower curve? So root x minus e to the negative 3x dx. If you need to keep more time on this, the other class, some of those wieners didn't get it, so they're behind you anyway.
Isabel office and even checking costs to the financial office.
From A to 1, from 0.238 to 1. Are we cool? Okay. Have a lovely day.